Hello everybody and welcome to this A-level chemistry video that continues the amount of substance topic. And in this video we will take a look at mole ratios and how we can use them in equations. We'll do some reacting mass calculations and work out a method for that. We'll work out how we can see which is the limiting reagent and which is the factor that is in excess. We'll move on to percentage yields calculations and we'll finish by looking at percentage atom economy calculations and implications. Before we dive into the real heart of this video, let's take a look at mole ratios in equations and how we can use them. So the first equation involves magnesium solid reacting with hydrochloric acid solution, making magnesium chloride and water. In the equation, the stoichiometric coefficients, that's the numbers in front of the formulae, they are 1 for magnesium and 2 for hydrochloric acid. And so these coefficients tell you the mole ratio that these chemicals combine in. So take 1 mole of magnesium and react it with 2 moles of hydrochloric acid, and you will make 1 mole of magnesium chloride and 1 mole of water. And so these mole ratios are very much like a proportion that you might find in a recipe. So this is like saying take 100 grams of one chemical and react it with 200 grams of another. Only in this situation we're talking about moles. So just like a recipe that you can scale up, you can do the same with moles. If we had 3 moles of magnesium, because it is a 1:2 ratio, we would need 6 moles of hydrochloric acid to react with it, and we would produce 3 moles of magnesium chloride and 3 moles of water. And so if you had 1.5 moles of magnesium, you would need twice as much hydrochloric acid, which is 3, and you would produce the same number of moles of magnesium chloride because it is a 1 makes 1 relationship, and a 1 makes 1 for the water as well. So we would have 1.5 of magnesium chloride and 1.5 of water. We can do the same thing for the second equation, just the numbers are different. The equation tells us that 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. And so if we didn't have 1 mole but we had 4 moles of propane, well then we know that the number of oxygen moles required will be 5 times as much as the moles of propane, which is going to give us 20 moles of oxygen, because the quantity here is 4 times bigger, and so the quantity here will be 4 times bigger. We've sort of scaled up our recipe by 4 times. And so we will therefore make 12 moles of carbon dioxide and 16 moles of water. We can do the same thing in the final equation. The ratio is a little bit more fiddly. We've got 3 moles of hydrogen, 1 mole of nitrogen reacting together in a 3:1 ratio, making 2 moles of ammonia. And so if we change the values and we had 18 moles of hydrogen, we would need to divide that number by 3 to work out the moles of nitrogen, and that would give us 6, because it is a 3 reacts with 1 ratio. And then the number of moles of ammonia that is produced is always twice as much as the number of moles of nitrogen used, which means that we're going to be producing 12 moles of ammonia. And here's one last really clever thing you can do with mole ratios. Because all gases behave in an ideal way, the same moles of one gas will occupy the same volume as another. Or, to say that differently, if we had 30 cubic centimetres of hydrogen, it would need to react with 10 cubic centimetres of nitrogen to produce 20 cubic centimetres of ammonia, because we need to mirror that 3:1 ratio of hydrogen to nitrogen and that 1:2 ratio of nitrogen to ammonia. And so it doesn't matter what we change the numbers to. We could have 72 cubic centimetres of hydrogen. What we need to do is we need to divide that number by 3 to match the stoichiometry, the mole ratio, and that would react with 24 cubic centimetres of nitrogen, and it would produce 48 cubic centimetres of ammonia. So knowledge of these mole ratios and the proportion that that represents is really important, and I'd also like you to have in mind that the mole ratio is mirrored for gases as well. We're going to take a look now at what are called reacting mass calculations. And what you do in these is you are given a known amount of one of the chemicals, could be a reactant, could be a product, and you have to use the equation, including the mole ratio, to work out what amount, normally mass, of a different chemical you would either produce or require. So let's have a look at an example. And so we have a situation here where you have iron oxide reacting with carbon monoxide to produce iron and carbon dioxide. And our question is, what mass of iron can be produced from 20 kilograms of iron 3 oxide? And the method that I want you to use here is called the box method usually, although you actually don't need to draw a box to make this work. And it always follows the same pattern, and it looks quite similar to how you calculate empirical formula. So down on the left-hand side, you have the following sort of subheadings. You have mass, you have MR, you have moles, and you have mole ratio. And you'll notice that this is almost identical to an empirical formula. And it's called a box method because in theory you should or could draw lines that produce a box like these. Now, some people call it the box method. It could also be referred to as a grid method because effectively what we're doing is we're making a table. And we're writing in now the information that we know. So I'll change my colour to black for information that we know. So we know that we've got 20 kilograms of iron oxide, and we know that we've been asked to work out what the mass of iron is that we could produce. So we need to remember our moles, mass and MR relationship here. And so we know that mass needs to be in grams for when we do this. So this is 20,000 grams. We need to be able to calculate the MRs of things. So the AR of iron is just 55.8. So really this is MR or AR, depending on what's appropriate. And then for iron oxide, we need to add up the 2 lots of 55.8 for iron and 3 lots of oxygen. And this gives us our answer here. And so to calculate the moles, we need to do mass 20,000 grams divided by the MR that we've just calculated. And when we do that, we get our answering number of moles. So what we've done then is we've worked down this first column to work out the number of moles of one of our chemicals. And the next job is to use the mole ratio, which we can find by looking at the equation. And the mole ratio has got 1 iron oxide producing 2 moles of iron. So that's just literally looking at the coefficients in the equation. And so our next job is to move sideways along here. So this is step 2, and to use that ratio and to say, okay, well, we make twice as much of our iron moles as we had of our iron oxide. So we need to multiply our 125.3 by 2, and we get 250.6 moles of iron should be produced. Now, we know that mass is moles times by MR, mass equals Mr. Moles. And so our final job then to work out the mass of iron is to multiply 55.8 by 250.6, and we get 13983 grams. Now, our final answer shouldn't really be to 5 significant figures, it should really be to 3. So 13983 to 3 significant figures becomes 14000 grams, because that 9 rounds up, that 8 rounds the 9 up to a 0, and then that 3 turns into a 4. And then in kilograms, depending on whether they'd asked us for this in kilograms, it would be 14.0 kg to 3 significant figures. And so this pattern is really repetitive for reacting mass calculations. You go down one column, along to another, and you go up the next column that we're interested in. And in fact, the 2 other columns are not necessary in this box method, usually. This next example approaches the issue from the other way round. Namely, we've been asked what mass of lead nitrate, here, this reactant, is needed to produce 500 grams of lead iodide. So we're looking at making 500 grams of this lead iodide. And so if we construct our grid as before, we can start to put our data in. So our target is 500 grams of lead iodide, and our unknown is what mass of lead nitrate do we need. And so our sort of redundant information, or our redundant columns, are these two here. And so what we're going to do, like last time, is we're going to go down one column, only this time we're going to go the other way. We're going to go back this way, and then we're going to go up to the top. And so to do that, we need to calculate our MR values, and lead iodide has an MR of 461. And then to calculate the moles, we do 500 grams divided by 461, and we get our moles value. And then we look at the mole ratio, and this time it's easier actually. The mole ratio is 1 to 1. And so the 1.08 moles that we want to produce here will be equal to the number of moles of lead nitrate that we need to use to make it. So 1.08 is required to make 1.08 because it is a 1 to 1 ratio. And then the MR of lead nitrate is 331.2. And so mass equals MR times moles. We need to multiply these two numbers together, and we get a final mass of 357.7 grams. And then two three significant figures, 358 grams on there. And so that is the mass in grams of lead nitrate needed to produce 500 grams of lead iodide. Let's take it up a level now and start talking about two quite complicated terms, limiting factor and excess. Now, the limiting factor is the chemical that gets used up completely because there isn't enough of it, and the amount of that substance that you have limits the amount of product that you make. That's why it's called the limiting factor, because its quantity directly influences the amount of product that you can make. Whereas the chemical that is in excess, that means that there is more than enough of this chemical, and so it won't get used up, and there will be some of this chemical left over once the reaction is finished. It's a bit like if you were baking and you had 500 kilograms of sugar and 500 kilograms of margarine and 1 egg, and you were trying to make fairy cakes. Well, clearly we have got two chemicals in excess here. The sugar is in excess, the margarine is in excess, and the egg, 1 egg, this is the limiting factor. And so it's this that limits the amount of fairy cakes or cupcakes that you can produce, 1 egg's worth of cupcakes. So it doesn't matter if we've got 500 kilograms of margarine or 600 kilograms of margarine, it's the eggs that in this case are limiting the quantity we can make in our recipe. Let's take a look now at 3 questions where we need to find out which is the limiting factor and which is in excess, and then use that information about the limiting factor to work out what mass of the target product we can make. So we're going to do this in the box method. I'm just not going to draw the grid. So we've got the mass of our chemicals, and we need to calculate the MRs, which are 2 and 38. And then the moles are going to give us 2 moles of hydrogen and 0.5 moles of fluorine. Now the ratio, we still need to use the ratio, is 1 to 1 from the equation. And what that tells us then is that the 0.5 is definitely the smaller value. And so this is the limiting factor. And the other chemical, hydrogen, is in excess. And so from here on in, we can ignore the hydrogen and we can only use the fluorine. So we've got 0.5 moles of fluorine. And so if we then track this along, the ratio of fluorine to hydrogen fluoride is 1 to 2. So our moles of hydrogen fluoride will be twice as big as our moles of fluorine, so it'll be 1. The MR of hydrogen fluoride is 20.0, and so the mass of hydrogen fluoride, mass is moles, 1 times MR 20, is 20.0 grams. If we then take a look at the second question, and if we've got 20 grams of each of our reactant and we calculate the MR values of hydrochloric acid, 36.5, and sodium hydroxide is 40.0, the moles of hydrochloric acid is then 0.548, and the moles of sodium hydroxide is 0.5. the mole ratio is 1:1 again, and so we can identify the sodium hydroxide as being the smaller number of moles, and the hydrochloric acid we can ignore for here on in. And then the sodium hydroxide is producing sodium chloride in a 1:1 ratio. So 0.5 moles of sodium hydroxide will produce 0.5 moles of sodium chloride, which has got an MR of 58.5, and then moles equals mass over MR, so mass equals MR times by moles, which gives us 29.3 grams of sodium chloride produced. So this is really exactly like a reacting mass calculation that we've just been doing before this page, except you've got the extra first step that you go down both of the first columns and then work out which set of data you use to carry on. This final question looks exactly the same, but there's an extra twist to it, so watch out for that. So the MR of hydrogen is 2, the MR of oxygen is 32. The moles then for hydrogen are 0.8, and the moles for oxygen are 0.5. Now it looks therefore that, like oxygen, is going to be our limiting factor, but the ratio of hydrogen to oxygen is 2:1. And so what that means is you only need half as much oxygen as you have hydrogen. And so 0.8 moles of hydrogen requires 0.4 moles of oxygen to react with it. Now we've actually got 0.5 moles of oxygen, which is obviously bigger than 0.4. So that means we've got more than enough oxygen. And so it is in excess, and the hydrogen is the limiting factor. To look at it another way, if we'd used up all of our 0.5 moles of oxygen, it would require twice as many moles of hydrogen, which is 1, which is obviously greater than 0.8. Further proof that the hydrogen is the limiting factor, and so what we should use moving on. Now looking at the mole ratio, 2 moles of hydrogen produces 2 moles of water, so in other words that's 1:1, which means that 0.8 moles of hydrogen will produce 0.8 moles of water. The MR of water is 18.0, so when we find mass equals Mr. Moles, MR times by 0.8 gives us 14.4 grams of H2O. So there you have it. That is how you work out which chemical is the limiting factor. Do be careful of the mole ratio when deciding, and otherwise the question is exactly like the other reacting mass calculations. Now the next idea we need to look at is the idea of yield. Now yield is concerned with how much of a particular chemical you have made or could make. And so yield just really means how much. And in a reacting mass calculation, they could actually literally ask you how much, or they could ask you to calculate the theoretical yield, or they could ask you to calculate the maximum possible yield, or something like that. And so there's different types of yield. There's the actual yield, which is what you actually make, and then there's the theoretical yield, or the maximum yield, which both mean how much you could make, and then last of all there is the percentage yield, and the percentage yield is how much of what you could have made did you make. Now I keep saying the word how much or amount, and this can either be in mass, in grams, or it can be in moles. So a theoretical yield could be 20 moles, or it could be 600 grams. You need to be prepared to use either of those quantities in an exam situation. And in fact, you also need to be aware of reasons why the actual yield is almost always significantly less than the theoretical yield. And that can be things like human errors that you can anticipate, or equipment errors, or specific errors for the experiment, like the reaction didn't fully finish, or there were some side reactions, or the reaction was reversible. You need to be mindful of the circumstances around an experiment and know which one to choose. And it's never really okay to just say human error. You need to say a specific error that is systematic in that experiment. In other words, it could happen each time, and there's not really anything that you could do about it. It's just an error that is in the experiment. Now let's take a look at how you actually calculate percentage yield. So to do this, it's reasonably straightforward. You need to know how much you actually made, and you need to know how much you could have made, and then divide one by the other. And so remember, this could be mass in grams, actual mass produced, divided by theoretical mass produced, or it could be actual moles produced divided by theoretical moles produced, or the maximum possible moles produced, and then multiplied by 100 because both of these are a percentage. And so if 600 grams was produced of a product, and we could have produced 800 grams in theory, as a percentage, that is 600 divided by 800 multiplied by 100, which is 75.0%. So the actual calculating of percentage yields is really nice and easy. Where it gets confusing is if they combine a percentage yield with a reacting mass calculation, which is what I'll do now. So let's take a look at a question here. What is the percentage yield if 600 grams of ammonia are made from 1200 grams of nitrogen? And so the instant thing that you will be tempted to do in a question like this is to say, brilliant, I've got my digits, 600 divided by 1200 times by 100 to get it as a percent is a 50% yield. And sadly, that is the wrong answer. The reason it's the wrong answer is that they haven't told you the theoretical yield. They've only told you the actual yield. So it's good to get into the habits of saying, right, okay, 600 grams of ammonia, that is what is actually made, because they've told us it is made. So this is the actual yield. And over here for the nitrogen, this is not the theoretical yield of ammonia. This is the amount of reactant. And that doesn't even appear in the percentage yield equation. We have to use that to work out how much we could get for ammonia. So our target for step 1, well, steps 1 to 3 in fact, is to work out the theoretical yield of ammonia in a reacting mass style question, because that's exactly what we've been doing in the reacting mass questions. So we need to have our mass, MR, our moles, our mole ratio down here. We need to populate this with the correct data. So we don't care about hydrogen, that's not part of this question. So for nitrogen, we know we've got 1200 grams of nitrogen. We know we want to know what the mass of ammonia could be. The MR of nitrogen is 28.0, and so the moles is 1200 divided by 28.0, which is going to be 42.86. If I'm going to report my final answer to 3 significant figures, by the way, I like to give earlier answers to 4 significant figures so I can then round at the end. If you're interested in tracking marks, by the way, that would be our first mark on a test question. And then the second mark will be for acknowledging that the mole ratio is 1 to 2 of nitrogen to ammonia, and so therefore the moles of ammonia produced will be double the moles of nitrogen that we used, so that will be 85.72 moles of ammonia, and that will be our second mark. And then our third mark will be for calculating the MR of ammonia, 17.0, and then multiplying it by 85.72 to get 1457 grams of ammonia. And that value, it will get as a mark, but what that value is, significantly, is the theoretical yield. So that's the maximum amount of ammonia that we could have made. But remember, we're told in the question, we actually only got 600 grams. So the theoretical yield is 1457. So the percentage yield is what we actually got, 600, divided by what we could have got, 1457, multiplied by 100, which gives us 41.2% yield to 1 decimal point. And so that's the only way it can get complicated is if they make you do a reacting mass calculation first, and then you'll get your 3 marks for your reacting mass calculation, which is standard, and then 1 mark for a percentage yield calculation. So this question would most likely be a 4 marker. The final idea we're going to discuss in this video is atom economy. Now, atom economy is a percentage value that indicates what percentage of our reactants are turned into useful products. So in other words, we can use that percentage to decide how wasteful a reaction might be. So we could get a 100% yield, but only convert a small proportion of our reactants into products, and so that might actually not be financially viable. Now, the atom economy percentage is really useful because it lets us know how many raw materials we're going to need and how effective we're being with the raw materials. And so if we make a small amount of waste, that's obviously really good for the environment, and we will have a limited number of byproducts that maybe don't have any particular uses. Now, of course, one thing that we can do is we can maybe sell on the byproducts depending on what they are and make an additional profit for our company. But if there are byproducts that are completely useless and maybe need to be disposed of, that will definitely increase costs further. Of course, the main reason, I think, why a high percentage atom economy is good is that it allows us to maximise the environmental protection that we have for our process. It maximises the sustainability of what we're doing, because if we're not producing very much waste, then this is more of a sustainable process than one that has a high percentage of waste. And so a high percentage atom economy is better for the environment because we aren't using up so much of the Earth's resources to make our product. And it also means that we're making fewer waste products that need to be disposed of, and hopefully minimising the harmful chemicals as part of the waste. And also it's better for society, because if chemical companies can make their products, maybe medicines or other detergents and things like that, in a more cheap, less wasteful way, then we will benefit from this as well, because the lower prices can be passed on and made available to the public. And so atom economy is one of the factors affecting whether or not we should do a process in a particular way. So we've got, of course, rate of reaction, so how fast we get our product; yield, so how much of our product we actually make; environmental impact or waste, which is the atom economy percentage; and of course overall cost, which we can't escape from. The company will definitely be interested in that. And so all of this feeds into the considerations of the company: cost and environmental impact, and how much product they actually can make and sell. Let's move on now to take a look at how we calculate percentage atom economy. Now, this first equation we've got here encapsulates the ideas from the previous slide really nicely. So first of all, there is only one product, and since there is only one product, this is 100% atom economy. However, you will recognise the reversible reaction symbol, which tells us that the percentage yield is definitely not going to be 100%. If we take a look at this second equation, which is the reaction of sodium hydroxide and chlorine to produce specifically sodium chlorate 1, which is used in bleach, and so a really useful product, and also sodium chloride and water as byproducts, we can work out the percentage atom economy from here. And just by inspecting the equation, you can see that we've got 2 sodium in our reactants, and we've only got 1 in our useful products. And similarly, there are 2 chlorine in our reactants, but only 1 in our target molecule. And it's the same principle for oxygen. There's only 1 in our target molecule, but there's 2 in the reactants. Now, the equation that we use to calculate atom economy is here. The percentage atom economy is the mass of the desired product divided by the total mass of the reactants multiplied by 100. So this is a case of working out the MRs of all the reagents involved, or at least the desired product and all of the reactants. And so we add together our sodium and our oxygen and our chlorine, and we get the target MR of 74.5 grams of sodium, oxygen and chlorine, so sodium chlorate. And then the sodium hydroxide, the MR of sodium hydroxide is 40, but there are 2 of them, and the MR of chlorine is 71. And so we need to add that 80 to the 71, and we get 151 grams of sodium hydroxide. Incidentally, this equation is balanced because the sodium chloride and the water add together to top the sodium chlorate up to 151 grams. So we've got 151 grams of reactant and 151 grams of product. But all we needed was the MR of sodium chlorate, 74.5, divide it by 151, and then multiply it by 100, and we get a percentage of 49.3. Always give your percentages to 1 decimal point, please. And so what that means is just under half of the starting materials that we've paid money for are turned into desired product. So there's a greater than a 50% waste. Let's finish by looking at 3 examples where we can calculate the percentage atom economy by setting the scene and saying which process should be used to make copper sulfate. Maybe we want to use it for a pesticide or something like that. So we've got 3 chemical reactions as shown here. The first one is from copper reacting with sulfuric acid to make copper sulfate and hydrogen. The second one has copper oxide reacting with sulfuric acid to make copper sulfate and water. And the third one has copper carbonate reacting with sulfuric acid to make copper sulfate and water and carbon dioxide. And so we calculate the percentage atom economy by dividing the mass of the desired product, copper sulfate, each time by the total mass of reactants. So have a go at those. Pause the screen. And if we have a look, the mass of copper sulfate is 159.6, and that's the same for all 3 of our calculations. The total mass of reactants varies each time, so the MR of these 2 adds together to make 161.6, and then the MR of copper oxide and sulfuric acid adds together to make 177.6. And then the MR of copper carbonate and sulfuric acid adds together to make 221.6. So in each case, those total masses of the reactants goes on the bottom of our calculation, and when we crunch the numbers, here are the percentages we get in each case. And so at first glance, it looks like we should definitely do the first process because it's got the greatest atom economy and so therefore the lowest percentage waste. However, what you might remember from before GCSE maybe even is that copper and sulfuric acid actually won't react together. Copper is less reactive than hydrogen, so you won't get a reaction taking place at all. So on paper it looks great, but in practice this reaction just won't happen. So we move on to the next 2. And the next one, well, 89.9%, still pretty high, not very much waste, but this reaction requires heating. It's really quite slow, so it's got a slow rate of reaction. So you might choose to move on to the third reaction because copper carbonate and sulfuric acid reacts instantaneously and it fizzes like crazy. So this is actually quite fast. So even though you've only got a 72% atom economy, you might choose to make the process quicker by using the faster reaction of copper carbonate. However, we've got one last concern, which is the environmental impact. This produces carbon dioxide, which contributes to climate change. And so it's a bit of a tough one, which one we'd use, and we'd need to know precisely the cost of providing that heat energy to make the second reaction faster, because producing energy to make reactions speed up also produces carbon dioxide, which again contributes to climate change. So it's a complicated issue, and there's no one factor involved. There's lots of different factors that we'd need to consider, all of them. The good news for you in terms of exam questions is that this will be really straightforward. They will give you an equation and they will ask you to calculate the percentage atom economy and maybe consider one additional factor, not lots like I've been mentioning here. Okay, that's the final thing we were going to cover in this video, so that's all done. We've covered a lot today. Well done. There was some tough stuff. I hope it was useful, and I'll see you again really soon. Bye-bye.